Hello everybody and welcome to week 11 of building scalable distributed systems. This week we're going to build on the information we've covered in the last few modules and talk about how the middleware technologies of the Java EE edition and the many other competing proprietary technologies have been modified to enable them to scale much more appropriately to the size and demands of current day applications. So the foundations of the middleware platforms we looked at last week really went back into the 1990s, but you will still see many of them available in systems that you work on, and many of these technologies or evolutions of them are still widely used as components in internet scale systems today. But for certain components, we need to really think about how to scale them to handle the massive amount of transactions and messages that we see at internet scale. And in this module, we'll just talk very briefly about two of these technologies which are available through the Apache Foundation. Kafka, which is an internet scale sort of message broker, messaging system, and Apache Storm, which is a scalable streaming analytics platform. So Kafka came out of LinkedIn and has been open sourced for 5 years or so now, and is also supported by a company called Confluent. Will give you support for this technology. So Kafka essentially feels like a publish subscribe technology, but it has some very different characteristics. Basically, it stores a stream of records in a topic, and a topic is just like we talked about before, basically just a number of messages published to a logical location. Each message has a key, a value, and a timestamp, and publishers publish to these topics and subscribers subscribe from them. There's 4 APIs. You'll see these when you play with Kafka in the class exercises. Each of the topics is essentially organized as a log. So messages are simply appended to the end of the log. And when you read the messages as a subscriber, you can start at the beginning and then just increment through them. You can also go back and identify earlier messages just by their index. Messages in Kafka logs exist until they expire. And so if you have an expiry date of 30 days, and a very high throughput topic, then you're going to have an awful lot of messages on your topic. You can also partition topics. So one logical topic can be partitioned into a number of physical topics. And the messages that arrive on that topic, potentially from many publishers, are distributed across the partitions on a round-robin basis using a hash function. Partitions can also be replicated for reliability and availability. Essentially a master-slave replication scheme. Publishers always send to the master, the leader in Kafka terminology, and the API returns by default when the message is persisted at all of the replicas, but you can configure this to give you slightly better latencies. Consumers read messages just as a stream, a sequence of messages. So they can basically read one and then ask for the next one. Or they can specify an index, which means they can go back in the message stream and process earlier messages. Consumers work very much like subscribers in a publish subscribe system. Except you can have these things called consumer groups. And a consumer group is essentially a logical single subscriber. But within a consumer group, you can specify multiple processes, which each will receive messages from one or more Kafka partitions. So in the diagram here on the right, you see that consumer group B is receiving messages from 2 servers, each hosting 2 partitions for the same topic. And because there's 4 partitions in this topic and there's 4 members of the consumer group, Kafka will make sure the messages from one partition go uniquely to a single member of the consumer group. So collectively the 4 will consume all of the messages, but each one just sees, one partition's worth, probably a quarter. In the other consumer group, A, see there's only 2 members, so Kafka will assign 2 partitions to each of the members of the consumer group. So again, collectively they act as a logical subscriber consuming all the messages, but the messages are distributed by Kafka across each of the members of the consumer group. And so you can think of this as actually adding an ability to scale subscribers. You can pull messages off a single topic, but typically in normal publish subscribe systems, you have a single subscriber pulling messages off a topic. This one you can have a logical subscriber which comprises multiple processes to process messages more effectively and efficiently. So Kafka is an innovation based on existing publish subscribe technologies. It persists things by default. It's a persistent technology. But by having multiple partitions, allowing replication for those partitions, it provides much more scalability and fault tolerance, and having subscriber groups as an abstraction paired with multiple partitions, it makes scaling of the consumption of messages much more effective and simpler. So this technology is designed to exploit clusters where you can replicate topics, and replicate subscribers. So I'll let you do more reading about this and play with the technology in the class exercises. Moving on, Kafka's kind of a streaming technology. It stores a stream of messages in its topics which can subsequently be processed. Sometimes you want to do processing on streams very, very quickly. Classic examples would be sensors. When you're detecting an earthquake, you don't want to wait 30 minutes to tell people there's an earthquake occurring. Financial transactions is another good one, whereby maybe you're doing credit card fraud detection and you want to flag a transaction as possibly fraudulent as quickly as possible. Another one, cloud node monitoring. If we have hundreds, thousands of nodes in a cloud, each pushing messages to some sort of stream processor, we want to make sure that we can do health checks very quickly so we can identify potentially failing nodes or components in our cloud. So we really need to be able to process these messages in flight before they're stored. We haven't got time to store them and then go back and process them. And this gives us what's known as situational awareness. Kind of real-time analytics is another way of thinking about it. So this range of technologies is very specialized. It serves a very important purpose in many applications. And here you can see just a diagram comparing 10 or so, 12 or so technologies that are available in this space. You see Kafka Streams appears there. Also appears is a technology called Storm. And that's the one we're going to look at. If you're interested in this comparison of the technologies, the URL's on the bottom there. So Storm was originally built by Twitter and open sourced 4 or 5 years ago. And it's basically a stream processing engine built around 2 main abstractions. A spout is a source of information, and a bolt is basically a node, a worker that processes information. Information in Storm is built on top of is processed by a topology. So what you do when you build a Storm application is you create essentially a directed graph whereby messages arrive at spouts and are pushed into bolts, which then process them. Bolts can be connected, and you can have fan in and fan out on bolts to make sure that messages can be processed and multiple messages can be sourced from individual messages. So you basically got a directed graph which runs forever, because streams typically, if you think of financial transactions, they don't stop. You don't stop doing financial transactions at 5 o'clock every day. So topologies essentially run forever. And what flows through topologies from spouts into bolts is what's known in Storm as a stream. So a stream is essentially a sequence of tuples, and tuples are just records, classes, objects, whatever you like to think of them. They can have built-in types, or you can have custom types and just provide serializers so that they can be serialized and passed from one bolt to another in the topology. So a spout is a source of tuples. So you can think of this could be a database, it could be a Kafka topic, it could be a log file or something coming in from sensors. And bolts in the topology can basically say, give me the next tuple from a spout. Spouts can be reliable or unreliable. A reliable spout can be asked to replay a message. And Storm, as you'll find out about in the reading, has a way to attempt to provide reliable processing of every tuple that is emitted from a reliable spout. Unreliable spouts you can't do this with. Obviously, you just get a tuple from the spout and it cannot be re-emitted, reread. So that might just be, a stream that's pushing stuff through some sockets or something. So a spout is a source of information. And a bolt is a worker process, a worker that processes the information that's emitted from spouts, consumes tuples, does some sort of computation, and based on that computation, it may emit new tuples, one or more new tuples into a stream. So typically these will do filtering, aggregation. You may run a very fast machine learning algorithm, a classifier maybe on some spam to see if it's a potentially spam email that's come in. You may do a database query based on the information in the tuple and augment that with some data that you read from the database, and pass it on for further processing to the next tuple in the stream. So basically you can build what says on the slide here is pipelines or graphs to perform complex multi-stage computations. And bolts and spouts are organized into topologies, where basically information sources are spouts and they flow through the bolts in the topology until they're fully processed. So in a topology, all the nodes run in parallel, and parallelism can be configured at every node. So when you define a bolt, you define the number of instances that you want to run of that bolt. So maybe if you specify 10 instances, Storm will basically run that bolt across 10 different JVMs within the system. Topologies, it says they never end. There's a way to kill a Storm topology, but essentially there's no terminate. And if you have a reliable topology using Storm's reliable processing feature, no data gets lost. So one interesting thing about topologies is if we have fan out, so a bolt receives a message and maybe it wants to split up the message to be processed downstream by multiple bolts. Maybe it's partitioning tweets to find out what words are in there and sending the words for further analysis that can be done in parallel. You can specify how the downstream bolts receive tuples from the upstream bolts. And so if a bolt sends a message to what's known as a shuffle group, then there's a random assignment to the downstream workers, downstream bolts. You basically just pick one and send it in, because there's no need to have any affinity of the tuples to the downstream bolts. Say there's a field grouping though. Maybe we want to send the messages to the downstream bolts based on some IP address range. So we can specify the IP address that's in the tuple, and this will then be routed by the Storm technology to one particular downstream bolt. So in that the same IP address value will always go to the same bolt. So it gives you a way to control which messages go to which downstream bolts based on their contents. Essentially, it's called content-based messaging. And you can also do an all, which sends the tuple to all the downstream bolts. This, of course, can end up flooding your network if you're not careful about what you're doing. And there's a few others as well which are less used, which you can look at in the document. So, have a play with Storm in this module and Kafka, and hopefully you'll get a feel for the ways that these technologies have evolved from the publish, subscribe, and messaging queuing technologies that we talked about in early modules to provide enhanced scalability, the sorts of scalability we really need at internet scale.